Hello and welcome to this video looking at the May-June 2018 paper for computer science. We're looking at paper 1 and this is version 2 of paper 1. So this first question is asking us to do something we studied at the beginning of year 10, which is to look at the different memory sizes. So here we've got to go from the smallest to largest. They've given us bit, so out the next one on this list should be nibble, which is 4 bits. Then we have a byte, which is 8 bits. Then we have a kilobyte, which is 1024 bytes. Then we have a megabyte, which is 1024 kilobytes, and a gigabyte, which is 1024 megabytes. This next question goes on to sticking with data representation, but looking at how images are stored. So here we need to list 4 points of how images are converted into digital photo files. So there's a clue of what you need to include with this word here, converted. So the first thing we need to mention is that there's a use of an analog to digital converter, converting the real world into a digital signal. So this is done by turning the image into pixels. Each pixel is given a binary value. You could also mention that these pixels form a grid that create the image, and that this binary value represents the pixel color. Again, you could combine this talking about a grid with talking about they are stored in a sequence in a file. You could mention the metadata, which we spoke about, which controls things such as the dimension, the resolution of the image, and also the color depth. You could mention that if you were talking about metadata. And you could also mention a suitable file format. So there's more than 4 points here. So I would say this one is very important to mention. I would say turning into pixels is very important to mention. Each pixel is given a binary value. I would say then very important information, and maybe mentioning an example file format. Now we're going to talk about how we can compress files. So we've got lots of very large files. She wants to reduce the files as much as possible, so there's a clue here. So the type we would go for here is lossy. That would be 1 out of these 4 marks. And now for the next 3, we need to explain how lossy compression would work. So remember, lossy would reduce the file more than lossless, because lossless, the file can be returned back to its original size, whereas lossy data is removed. So what we're doing is removing redundant data. So this could be like very, very small, insignificant changes between colors. So you could make them 1 shade of red instead of 8 shades of red. You can still have images of the same quality. Most images that you look at online, which are JPEGs, have been lossy compressed, and you very rarely notice any issues with them. Again, there's no requirement in this that the files need to stay the same size. So she's not said I want to compress them, but I want them to be the same size in the question. Again, I would say these answers here. So lossy will reduce the file size, redundant data is removed, and I would also say photos can be sent quicker, faster to upload, faster download. Something along those lines would be the easiest ones to remember here for the exam. Now we're going to look at binary. So stopwatches uses 6 digits to display minutes and seconds. So we're going to use an 8-bit register to represent each one of these numbers. So it's going to ask you to convert hours into binary, or 02, and then 31 and 58 into binary. So I'm going to put the binary grid up. So you can see that 2 is just 2 in binary here. So 0, 1, and because it's asking for 8-bit, you've got these boxes, I would recommend that you do the rest of the zeros in here. So 31, again, we can't use 32, so it's going to be meaning we're going to have to activate the 16, 8, etc. So here it's 16, 8, 4, 2, and 1 would give us 31. And then this last one here, 58, would be 32 plus 16 plus 8 plus 2. So remember, if you are doing these binary questions, you need a little support. Ask for some paper in the exam, and you can draw the binary grid and help you to do your calculations. Sticking with the same theme, now you've been given some numbers in binary, and now you need to convert them into denary values, which is base 10. So I've just popped the binary grid on top of here to help you with the conversion process. So the hours would be 4 plus 1, so that would give us 5. The minutes would be 16 plus 8 plus 2, which gives us 26. And the seconds is 55, so 32 plus 16 plus 4 plus 2 plus 1. Now we're going to work in hexadecimal. And we have, remember that each one of these is represented in a nibble. So just remember the hexadecimal runs from 0 to 15, 16 characters. It's base 16, so 0 to 15 is 16 digits. And again, 0 to 9 are the same. And then 10 becomes A, B, C, D, E, F. So I'm going to put the nibbles on top of these boxes. And remember, each one is 1, 2, 4, 8, 1, 2, 4, 8. So if I was going to convert 3, just like this, 2 and a 1, then converting this next part, which is a 0, which would be all zeros, none of these are activated. And then D, we need to look for 13. So 8 plus 4 plus 1 would give us 13. So just remember, if you work using hexadecimal, we're just dealing with nibbles. So 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. Please don't go 1, 2, 4, 8, 16, 32, and build up and keep multiplying by the powers of 2. You need to make sure you're using nibbles. Again, a parity bit question. These are relatively straightforward. People get a little bit confused here on the what to write for the explanation, but we'll go through that in a second. So here we need to check that only one binary number has been transmitted correctly. So we need to check the parity. So the parity bit means this lets you know if it's going to be odd or even parity. So how many, what's being used to control it. So how many ones should be in the code, and if it should be odd or even. So 1, 2, 3. So this one's odd parity. 1, 2, 3, 4, 5, 6. So that's even parity. 1, 2, 3, 4, 5. So this is odd parity. So it says only one has been transmitted correctly. So that means register Y is the only one with even parity. All we have to do in the explanation is pretty much just say what we did. So we counted the number of ones and zeros for each byte. We compared them. We knew that it should be even parity because only one of them should be that. And the two with an odd number should have the different combinations here to make them even or odd. Or sorry, to make them all even. So you just need to basically say what you did, that you went through, checked each digit, checked the parity bit, checked if it was even or odd, and say that's how you spotted the one that was wrong. So now we have a fill in the blank exercise. There's quite a few words here, so let's go through this step by step. So the central processing unit, CPU, something's the data and instructions, which means it fetches them and needed, and it stores them in the immediate access store, or IAS, to wait to be processed. So this immediate access store is also can be considered the RAM as well. So that's where files are waiting to be processed. The program counter holds the address of the next instruction. This is sent to the MAR. This then comes to the MDR. It is then executed. Any calculations are done by the ALU, and any results are stored in the accumulator, ACC. And we're going to move on to a logic gate question. I can't draw the logic gates out in PowerPoint, so what I'm going to do is I've created it on Logically, so you can see how we've broken this down. So here we're going to go for this XOR, which means an exclusive OR, which means only 0, 1 or 1, 0 work. 1 and 1 doesn't activate an XOR, it only works on the OR statements. We've got OR B as 1, so we've got this here. So we've got the OR here coming in for this section here, and then we have this combination here. So A is 1 and C is 1. So we've got this part represented here, and that feeds into here to make this complete bank of statements. Then at the top we have NAND C is 1, and then we're going to read backwards. So NAND, so C is 1 coming in here, and then A is 1 coming here, and B is not 1. So B coming in, not 1. So remember with these statements, what you have to do is you read from here, then you split it, and then you work backwards to see how they should be represented. Now what we do is we work through the truth table. So 0, 0, 0. So this would be 0, 0, 0. So nothing, nothing. This would be 0, so that becomes 1. That's 0. So this would be 0. This comes in here. So we would have 0 and 0. That would get us a 1. As you can see, that's already activated here because it's a not and. So 0, 0 would get us a 0 usually because it's a not, it's been inverted. And then then we get 1 and 0 coming in, which is activating this. And you just need to go through the same process where you just put each one of these inputs through the circuit. If it helps, you can use this working space or ask for a piece of paper, or I usually just write the 0s and 1s and cross them out. You're not going to lose marks for showing you're working out on this area, as long as you don't, as long as your working out doesn't make your diagram less clear for the examiner to mark. Now we're going to look at translators for high-level language. So we want to make sure the program is executed as quickly as possible, and we want to send the machine code to its friend. So for this we would use a compiler. We want to make it into an executable file, sorry. So the explanation for this would be once it's been compiled, it doesn't need to be recompiled, therefore it can be executed faster. It's going to give them an executable file, which allows them just to send the machine code because it's already a program ready to be run. And it's also advantages that Dimitri's friend doesn't need any software for compilation because it's already been done for him. So the clue here, I would say, is in the word executed as quickly as possible, because only a compiler produces an executable file. So now we have to look at this type of barcode, and we should know that this type is a quick response code or QR code. And now we need to explain how the data is stored in a QR code. So usually you have to scan this with some form of app. This would be usually built into a camera. These three large squares are used for alignment. These black squares, again, would reflect less light. So the app would be able to process this image, and it would convert the signal that's coming in from the light sources into the pixels, which will be converted into binary values. So now we have to explore how a capacitive touchscreen works. So a capacitive touchscreen has a conductive layer, and an electrostatic field is created. So when you touch the screen, the charge is transferred to the finger, and the location of this kind of completed electrostatic circuit coordinates the position that's been touched. Now Alexandra is wearing gloves, and we need to know that the conductive layer, the capacitive touchscreen doesn't work because gloves are an insulator, therefore the electrostatic signal can't transfer. So you're blocking the charge and you're stopping the field being transmitted. You can get special gloves now which have this built into them, but standard gloves don't allow this circuit to be completed. So now we need to explain how Alexandra could use her mobile device while still wearing gloves. She could have a stylus, she could use the special capacitive gloves, or this is a bit of a long shot here. I would say the stylus and buying the special gloves would be easier ones to think of, but they're also saying that she could use voice commands if she wanted to do vocal commands or voice commands for her device. Now we have a question. If you're looking at questions where they're talking about sensors and the microprocessor and they're around 6 marks, you usually have to mention a few key things. So you usually have to mention a suitable sensor if they don't mention one in it. Some questions about fish tanks mention that it is a pH sensor, so that would be fine just to use the sensor that they speak about, but in this case you've got to state one, so a motion sensor or an infrared sensor would work. You always have to mention this, that the data is being converted from analog to digital, though it's been sent to the microprocessor. This is an essential thing to say as well. Then, depending on the question, you would say the different comparisons. You have to mention that it's compared in the microprocessor. And in this case, if the data is out of the range, the light goes on. You would then wait a suitable period to see if no motion was detected, and then the light would turn off. And you have to mention it's a continuous loop. So let me just get my highlighter. I would say this, and this you always have to mention, and depending on the question, like this section here is going to change, so you just need to think about what a security light or kind of like a fish tank sensor would do, and put some sensible comparisons in here. Sometimes it will give you clues in the question, other times you just have to think what's a sensible thing to include in this section. Okay, I haven't done my animation or formatting here, but again, how could email be sent more securely? We're using encryption. Encryption works, basically you have the plain text, you encrypt it using an algorithm. The plain text is given a key, the encrypted text has a key, which is the cipher. The encrypted text is the cipher. You then would send the ciphertext and the key, and you'd be able to use that key to decrypt the ciphertext, and that would turn it back into the plain text. Again, it's mentioned a parity check earlier. Usually, when it asks you to mention other error checking methods, it usually goes alongside the parity checking question, but they've separated them out here. So again, you can mention a checksum, and knowing that you calculate the calculations carried out the data to produce the checksum. You are sent the same data and the checksum, so you recalculate it, and if your checksum matches the checksum you were sent, then that means it's been transmitted correctly. If there's an error, then you need to request the data again. Or we could say ARQ, which is automatic repeat request, which sends acknowledgements and times out. So you are sent an acknowledgement. If it doesn't receive if it doesn't receive the acknowledgement that you received the data back, it will then send it again. So if no acknowledgement is received within the time frame, it says that it never was received, and it sends the data again automatically.